Hi, welcome to IB Chemistry. Today we'll be talking about chemical kinetics and introducing you to the ideas of rate of reaction and how we measure those rates of reaction. So the very first thing that we need to do is talk about what is rate of reaction. Most of you talk about rate of reaction as how fast a reaction takes place, but how fast is not really easily defined. What does that fast mean? Well, the rate of reaction is the rate at which the concentration of a species changes, i.e., is the change in the concentration of a species, a compound, over a certain period of time. So for example, if we were measuring rate of reaction with respect to species X, well, the change in the concentration of X over the amount of time through which that it took for that change to take place is going to be our rate of reaction. Now obviously delta concentration of X is going to be the concentration of X final minus concentration of X initial. That's always how we define our deltas, our change in concentration. So for example, if we had a reaction such as A goes to B, the rate of reaction with respect to B would be the change in concentration of B, product B, over amount of time T. Alright, now we could equally well define the rate of reaction with respect to A. Now to do that, we would write it such way as but notice that the change in the concentration of A, because A is a reactant, would be negative. So in order to make them really equal to each other, we must introduce a negative sign. That negative sign is there, so when we're talking about, or when we're measuring the rate with respect to a reactant, we are going to make sure that we still get a positive value overall. All right? Now, if we were to graph the changes that are taking place in the reaction, all right, again, the reaction is just A goes to B. As A is being consumed, we're going to have some initial concentration. In this case, I'm going to call it 1. All right, and that initial concentration is going to be here, and it's going to yield a decreasing curve. We see that the concentration of A is going down. Similarly, at the same time, the concentration of A is increasing because the stoichiometry of this reaction is 1:1. The two lines are just mirror images of each other. They just basically flip through a horizontal axis. All right, so you're just going to flip them up and down. All right, now that's all very pretty, but how is it then really that we measure rate of reaction? Well, we could do an average rate of reaction, and I'm going to show you again a little just something that I've written here. The average rate of reaction would just be, the amount of change in the concentration of either A or B over a given period of time. So we would measure, let's say, for B, here and here. And we can then take those points and do your typical calculation and of y2 minus y1 is over x2 over x minus x1. All right? And that's the same thing as saying change in the concentration of B over change in time, which we've defined as rate. That would be an average rate. If instead we were interested in the rate at any one particular moment in time, we need to use a little bit more exact methods, and we will have to use a little calculus. Don't worry, we won't be doing too much of that, but we can measure it by saying, okay, I want a particular point. I want the rate at that green point that I've put. Now let's say that I do it with respect to A. Well, the instantaneous rate would be equal to the slope of the tangent to that point. And so the slope of the tangent equals the instantaneous rate. We will continue talking a little bit about that later. But first, we need to learn how can we measure the rates of reaction. So that's the first things that we're going to do. And so let's look at some experimental methods for doing this. One of the easiest way to do it, if you have a reaction that produces a gas or consumes a gas, you can measure the change in volume of the gas or the change in pressure in the system. And so there are several different ways in which we can set this up. As you can see from the image, if we have a reaction that produces a gas, we could just literally have it in a closed container connected to some tubing, and then we can have the gas displace over here the amount of liquid that would be present there. All right, and so if as the bubbles of gas come into the fluid-filled liquid cylinder, they would displace the liquid, and we can measure how much gas has been produced. Now, since volume is directly proportional to the number of moles, all right, when we're talking about gases, that should serve as a way of measuring the rate of reaction, because we can find out how many moles of product have been produced in a certain unit of time. All right, so that can be easily seen, and here is a little animation of how that would work. So in this case, we have marble chips, which are just calcium carbonate reacting with hydrochloric acid. That reaction is a neutralization reaction which would produce water and carbon dioxide plus a small amount of calcium chloride. Now, as the reaction takes place, gas is going to be evolved and it should displace this. So let's look how this would look. All right, and as the reaction starts, time's going on. All right, we are producing gas bubbles. You can see how they start displacing the volume of the liquid, and as the reaction stops, we have the amount of carbon dioxide that has been produced. We have a moles. If we have the pressure and the temperature, we can calculate, if we have the volume and we have the temperature and pressure, we can calculate the number of moles, and therefore the change in the amount or the concentration of carbon dioxide that's being produced. That should serve to give us a great idea of what the rate of reaction is. Now, we can also do this not only through the process of measuring displacing gas, but you could also use what is called a gas syringe. If we have a gas syringe and the gas is being produced, the volume, the syringe is going to move and be displaced by the volume of gas that is coming in. That method is useful if the gas that you're producing will react with water. So for example, if you had a gas that is highly reactive with water, like carbon dioxide, in fact, in the previous example, it is not ideal because carbon dioxide does react with water and some of the gas would be lost. You would be better off, you'd be better served by having a gas syringe and then show that this way. So let me show you what that would look like. All right. So in this particular place, we have the same reaction, but now we have a gas syringe, which is placed horizontally, so the weight of the plunger does not affect the reaction or increase the pressure. Again, if we have the reaction taking place, you see how it slowly displaces the plunger. We can measure the volume of gas being produced, and if we have the volume, the temperature, and the pressure, we can calculate the number of moles and once again calculate exactly what the rate of reaction is. These graphs that are producing gas, it could be by measuring where the volume of the liquid was. So the burette, for example, or the graduate cylinder could have been filled to 50, and as the reaction takes place, this is the amount of liquid that is still present in your container, in your volumetric, in your graduated cylinder or your burette. So that means that the reciprocal of that, all right, or the inverse, would be the volume that is being occupied by the gas, all right? Or in other words, the volume of the gas is increasing with time as the volume of the liquid is decreasing with the time, all right? So those are different easy ways of looking at that. A second method which we can use in order to measure the rate of reaction is to measure the change in mass that is taking place over the reaction. So let's look at how that one would look. All right, and again, I have a little animation on this. So if we have our sample of marble chips and hydrochloric acid, we're going to have it in a container. We're going to put a little of cotton wool just to allow the gas to escape, but none of the acid spray to actually leave the container, because that would change your mass. Now we're going to tar our scale so it's a 0, all right? Or you can have the initial value, but it's easier just to tar it to 0. And then as you run it, what's going to happen is that the gas is being evolved, is going to escape through the cotton, and therefore you see how our mass starts decreasing. If we measure the change in mass over the time, we have an alternative way of calculating rate of reaction, because given the mass, we can calculate the number of moles of gas that are escaping, and that is also a way in which we can calculate rate of reaction. Now, for other types of reactions, you could as well, if we are to have a reaction in which we are consuming ions or that we're producing ions, that would be a type of reaction that we could use a conductivity probe. And so if the conductivity increases, it's because we are forming ions. For example, in the reaction between weak acid phosphoric acid and weak base ammonia, the products that are made once we balance the equation are going to be ionic products. We're going to make ammonium phosphate. Let me show you how that looks. In aqueous solution, ammonium phosphate ionizes or dissociates to give you these two ions. So we've gone from a solution that has very few ions initially and would have a very low conductivity, like it's shown in this graph, to a solution that rapidly increases the number of ions present and therefore the ability to conduct electricity. So this is another way in which we can measure the change in the concentration. So it's an instantaneous method. It's a way that we can see it as it's taking place. There's no need to make very long calculations. All right. Now we can also be looking at changes of pH. All right. So as the reaction takes place, as for example a species that is acidic is being consumed, we can also measure that. In this particular case, we have a reaction in which we're going from a low pH to a slightly higher pH. So this could also be a way of measuring, just like we had done the previous reaction, but instead of measuring conductivity, we're measuring the pH. It could be done for any simple reaction in which we're reacting a base, let's say sodium hydroxide, with an acid such as hydrochloric acid to give you water and sodium chloride. So if we are measuring the initial pH of the hydrochloric acid and we start adding the sodium hydroxide, we can see how that change of pH takes place over time, and it would be a way of measuring how quickly that process is taking place. All right. We can also do a couple of other things. We can measure the change in concentration by what is called quenching and titration. Quenching is stopping the reaction cold. So you take a small sample of your reaction mixture, all right, and you're going to chill it very quickly. That's one of the easiest ways to quench a reaction, because as you lower the temperature, the rate of reaction becomes very low, so you can measure then the concentration of reactants or products. Let's say that you're having a reaction with an acid. If the reaction is consuming the acid, you can quench the reaction at some point, measure how much acid is still left over by titration, all right, and then later on take a second sample, quench it, measure how much acid is left over, and you can see what the change in the concentration was between the time that you took those 2 points. So that is taking advantage of the fact that you can take several readings at different points in the reaction. I can take a sample here, a sample here, and a sample here, and see how my concentration of reactant changed. But the important thing is that you have to make sure that you can stop the reaction. And that's what quenching does. This method is particularly difficult to do in a high school lab, and one of the reasons why we tend not to use this method at this level. But if we had liquid nitrogen, or at least dry ice, we could take our small sample, put it in dry ice, put it in liquid nitrogen to stop the reaction cold, all right? And then we could then titrate slowly, or do some other use of instrumentation. We could do NMR, we could do infrared spectroscopy to find what amount of the substance is still left in there. Once we have that, we have the concentrations, we can calculate the changes. All right? Finally, we have 2 more methods. We could be following the reaction and see the change in transmission of light, which is called spectrophotometry. So as we pass a light, all right, as we pass light through a sample, the samples that are there may absorb certain frequencies of light, and therefore a smaller amount of light will go through and be measured by the detector. So if we had a number of compounds, here for example is the absorbance that these compounds have for certain different wavelengths of light. Okay, so some compounds may absorb more in the violet region, some more in the green region. The colors that you see in the background are the actual colors that we are, or we have compounds that absorb very well in the orange-red region of the graph. Now, you want to select a frequency or a wavelength at which the compound will have relatively high absorbance. So as the concentration of the compound changes, you can then see how the absorbance changes. So the more concentrated a sample is, the greater the absorbance it will have. Now that is called Beer's law, and it's linear for many compounds. It's not linear for all compounds, but if your compound follows Beer's law, you should be able to calculate the concentration of the compound from the absorption. If you can see how it changes over time, then you have a way to measure rate of reaction. All right, here for one compound, I'm showing you the absorptions or the maximum intensities, all right, which is the inverse of that you would get for the different frequencies of light. So this particular compound absorbs in the violet region, very small absorption in the blue, a little bit higher, but absorption in the green, a quite high absorption in the yellow, and quite high absorptions both in 2 different regions of the red colors. All right. So you always want to choose, for this particular compound, you would either choose this yellow absorption here around 620 or this red absorption about 710. All right, because these are the two highest absorptions, so we give you the best data if you want to see how the concentration is changing. All right. Finally, we can make a determination of how fast the reaction is taking place, not by measuring exactly the rate or the concentration, but saying, okay, once this reaction reaches this certain point, I'm going to say that the reaction has stopped, and I'm going to see how long it takes to get to that point. Even though we're not measuring concentration, it is directly proportional to the rate, and therefore we can make all the important decisions about how the rate is being, how fast the rate is based on that. So let me give you an example of this. All right, and here we have it. All right, in this particular reaction, we are going to be reacting thiosulfate with acid, and in order to produce colloidal sulfur. Colloidal sulfur makes things opaque. So we have a start with a clear solution in which we can see the X. Our end point is going to be, we're going to say that it is the moment that we stop seeing the X. All right. So as we react this and we start measuring the type, we see how the reaction, the solution becomes more opaque, and to a certain point, as we say, now the reaction has stopped because I no longer can see the X. And that would be the time that it takes to do that would be consistent to the concentration of the particles of colloidal sulfur. All right? So it does work to do this. So from here, next time we're going to talk a little bit more about how and what we do when we're calculating rates of reaction. But at least we now know how to measure them. Thank you.